This is my presentation for Lab 4 from Physics 2211. The goal of this experiment was to analyze the predicted and observed motion of a mass spring attached to a fixed point. In this lab, the spring force was used to predict the motion of a mass spring system, and a constructed computer model was used to analyze the observed and predicted data. Finally, the position data was used to create and analyze energy changes. Overall, the final results showed that the data created by the computer simulation and the tracker created similar results. Finally, the oscillation time for the y component of position was shorter than the x component. This lab has many fundamental concepts that are crucial to the understanding of the computer simulation. First, Newton's second law of motion is used throughout this lab. Newton's second law of motion is described using the following equation. Velocity final equals velocity initial plus net force divided by mass times delta t. Next, the spring force was important. The spring force uses the spring stiffness and the absolute value of the stretch of the force to determine force. Finally, the energy principle was used to describe the changes in energy using the following equations. Delta E equals delta K plus delta U. Delta U equals delta U of gravity plus delta U of the spring. And U of the spring equals 1/2 Ks S squared. I recorded a few calculations from the lecture video begin the tracker and computer simulation. The time of oscillation was determined to equal 1.524 seconds. The spring constant equals 6.83 newtons per meter. The stretched length of the spring equals 0.123 meters. In order to complete this lab, the tracker computer program was used. I analyzed the videos that were pre-recorded and uploaded it to Tracker. From there, I determined the correct placement for the x and y axes. For each video frame, I determined the object's center of mass in order to collect the position data values. As you can see, the position versus time graph shows a pattern of oscillation. This is due to the nature of the spring and the spring force. This is the code I used for the first computer model. I began by copying the starter code into GlowScript. From there, I made the changes necessary to properly construct the simulation. The arrows point to each of the changes I made. First, I updated the position's mass, which was 0.402 kilograms. Then I updated the ball's initial position, which I obtained from my initial position value from Tracker. I kept the ball's velocity at 0. I updated the spring constant and the relaxed length to the values I previously discussed. Then I updated L to equal the ball position minus the spring position, L hat equals L minus the magnitude of L, and S equals the magnitude of L minus L naught. Then I updated the equation for the force of gravity. In the y component, it equaled negative mass of the ball times gravity. I updated the force of the spring, which was negative Ks times S times L hat. And then I updated the overall net force, which is the force of gravity plus the force of the spring. Next, as we've done in previous labs, I updated the ball's velocity and position equations. Finally, I updated the kinetic energy to equal 1/2 times the ball's mass times the magnitude of the ball's velocity squared. The potential energy of gravity, which equals the ball's mass times gravity times the ball's position in the y direction. I updated the potential energy of the spring to equal 1/2 times Ks times S squared. Finally, the total energy of the system equals K plus the potential energy of gravity and the potential energy of the spring. These are the graphs that the computer simulation created. The first graph plots the changes in energies versus the change in time. The blue line represents the change in kinetic energy, the green line represents the change in potential energy of the spring, the red line represents the change in energy of gravity, and the orange line represents the total change in energy. The second graph plots the change in position versus the change in time. The red line represents the tracker data, and the blue line represents the computer simulation data. As you can see, the red and blue lines follow similar patterns. However, they range over different spreads, which is likely due to the variance in the lecture video data from the data I collected from the tracker simulation. Again, the graph on the left represents the tracker data from the code, and the graph on the right represents the actual tracker data. As I stated before, the red line in the graph on the left represents the tracker data, and you can compare the different graphs. They seem to follow similar patterns of oscillation. The energy principle is satisfied because it states that the change in energy in a closed system will equal 0. In the graph, you can see that the total energy, which is the sum of the kinetic energy, the gravitational and spring potential energies, equals approximately 0 at all points on the graph. The second discussion question asked us to compare the x-coordinate points with the y-coordinate points. The oscillation time for the x-coordinates was 1.614 seconds, and the oscillation time for the y-coordinates was equal to 1.36 seconds. The oscillation time for the y component is less than the x component because there are more forces acting on the y component, such as the spring and gravitational potential forces. This concludes my presentation for Lab 4.